Okay, welcome. Hey, Susan, Jordan, Jacob, and Ralph and Victor. This is actually our very last day of new material for linear algebra. So it's kind of a big day. And let me share my screen and talk about what new material we'll do. Okay, so the plan today, as always, I'll start out with questions. That could be your homework or whatever it is that you might be asking about. Could be about the presentations. And then we're going to get into more of the same. So we're kind of finishing up all the stuff that we did for matrices, but now we can do for linear transformations that are general linear transformations. So we'll talk about the kernel and image of a linear transformation. We'll talk about the rank of a linear transformation. And we'll talk about coordinates. So we'll talk about coordinates and how those coordinates work with linear transformations. And in particular, since you can talk about coordinates from one vector space to another, we can talk about the matrix that moves the coordinates from one vector space to another based on the linear transformation T. So that's a big deal. And we're going to spend a lot of time on the matrix of a linear transformation today. And then we're going to talk about composition of linear transformations, and in particular, how that relates to the matrix. And it's basically the same stuff we've already done, but now we're doing it again for general spaces. And then we'll talk about isomorphisms. So we'll talk about if you have an isomorphism of a linear transformation, what do you know about the matrix? There should be no surprises today, at least in terms of these sections, until we get to the last item, which is actually not in the book, but it's important enough that I couldn't live with myself if I didn't go over this in a linear algebra class. It should be in the book. So I'm going to talk about it just for a little bit, but it's a very deep subject, and that is inner product spaces. So for example, if you have two vectors and you want to find out how far apart one is from another, do we know how to do that? Do you know how to find out how far one vector is from another? Kind of a distance function? Any thoughts?
We can for vectors in Rn.
Right, we can for vectors in Rn, and how do you do it?
Isn't it the magnitude distance formula?
It's the magnitude, but what's the definition of the magnitude? And the key is you don't need the distance formula.
The square root of all of the bases taken to their squares.
Okay, but again, you have two different vectors, so there's a better formula than what you're thinking about. Okay, yours is kind of works, but it's not as nice. You take the dot product of the two vectors. Do you remember that? So you take the dot product of the difference of the two vectors and then square it. So if you want to find out how far apart it is, that's how you do that. Or take a square root of it, sorry. You take the dot product of the difference of the vectors and then you with itself, and then you take a square root. So it turns out that's what we're going to be doing. But we're going to be doing it not with a dot product because there is no dot product for general vectors. We're going to have what's called the inner product. Okay, so that's the last thing we're going to do. So I want to mention again, we're getting close to the end, and I want to talk about calendar. So the first thing is, again, today is the last day of regular class. So it's the last day where I'll be going over new material. And then Friday, I'll answer questions about homework because there's homework due on Friday. And then I'm going to review for the final exam, which actually, honestly, I haven't written yet. I'm going to write it tomorrow. So I can't even tell you details about it yet, but I will review about the final. I can tell you when it is, and that is Friday, a week from Friday. Okay, and then Monday, what happens Monday?
Presentation.
Yeah, Monday are the presentations. So that, just to let you know, to remind you, they're 20-minute presentations. And then I think I didn't mention it, but right after your presentation is done is Q&A time. So that's when your classmates or me ask you questions. Okay. And I do encourage you all to ask questions, things that you might be interested or curious about. And then the idea is that hopefully when you're preparing for your presentation, you've learned a lot about the topic and you can answer some questions. And that doesn't mean you can, know everything, but at least you can answer some things. And if no one asks anything, then I'll ask something. So it's always better for you to ask each other questions. So otherwise I ask hard stuff, just a warning. So it's better for you to ask questions. So, be ready for that. And I don't know how long it's going to go exactly, but if they're 20 minutes each and there are 4 groups, that's 80 minutes. And our class actually officially goes for 105 minutes. So there'll be time for questions. There's no homework due that day, so we can jump right to the presentations. So there'll be time for questions, and we might even end early, depending on how it goes. So that's the plan on Monday. Wednesday, I have not heard back. I sent another email, still haven't heard back. So there's a good chance it's not going to happen for a week from today. But if it does happen, I'll let you know by Friday. If not, then we won't have it. Because again, I have to get permission from the college and they're dragging their feet. So I apologize. I'm doing what I can. So we may not have, a face-to-face review session. And if we don't, we don't. But Friday is definitely a review session. But I thought it'd be nice to have an online review session. And then if we could, a little extra review session that is face-to-face. And if we can't, we can't. Hopefully you'll understand. But I've tried. So that is the plan for the rest of the class. And that's about it. I want to mention one more thing, and that's Math 119. Do you know what that is? Anyone know what Math 119 is?
I don't think that's Diffie Q.
It's not Diffie Q. Diffie Q is Math 204.
Is that statistics?
Nope. It's not business calc. All right, I better tell you because you're not getting it. All right, so on April 20, I think it's 4th or 5th. Let me grab my calendar. Just a minute. April 24th. So on April 24th, we will have, there's a conference. And it's the California Math Council Community College Conference. And it's on applications of mathematics, fun stuff you can do with math. And I have created a half-unit course. Basically, you register for the class. You obviously not go to the conference because we can't do that, but we Zoom into the conference. And then you'll get your half unit, and it'll be the easiest half unit you've ever had. All you have to do is Zoom in. Okay, there's no final exam or anything like that. It's just a half day class, and again, it's a nice easy class. I want to let you know I'm the instructor of it officially, but also more importantly, I'm the chair of the whole conference. So if you register for the class, I promise you that if you show up and Zoom in, you'll pass the class. That's all you have to do. And it's for that day. And you're all welcome to, encouraged to show up. And there's some really cool applications. There's going to be 3 main presentations. And there's also going to be, which I'm leading, a little game playing, little gambling game playing that I actually finished up this morning. So I want to let you know that, again, that's a nice one to take. Looks good on a transcript. It's a freebie. And I think it's a half unit, something like that. So easy to do. Any questions about that class? And it's called Applications of Mathematics, by the way. So nothing like this class in terms of, how much stress you have and difficulty and all that kind of stuff. Any questions? And it's free, by the way, to register for the conference. So that's always a good thing. Any questions? Okay. If you have questions about it, ask me anytime, office hours or email or whatever. registration for the conference. I believe it or not, I don't have a link because literally it started 1 minute before this class started because Daryl, who's in charge of that, just set it up and sent an email out 1 minute before it started, and haven't had a chance to even go to the link. But there is a link and I can send you that link to register. Registering for the conference is different than registering for the class. They go together if you want the half unit, but just registering for the conference is different. That's not part of the class. Okay, but you have to do it to be in the class. Any questions about anything? And that could be the homework too. Any questions about homework or about upcoming events? Question 5 from 9.7. Okay. The good news is because I wrote it, it's in a Word document, and I just literally before I even got here, I copied and pasted the whole assignment here. So 9.7, number 5. Okay, so what we've got is let A be an M by M matrix, that's a square matrix, and consider the linear transformation T from the vector space of M by N matrices to itself defined by T of M equals AM. Okay. Let me see something. Yeah. Prove that T is an isomorphism if and only if A is invertible. Okay. So do you understand the question first? Any questions in the question? Any questions? Okay. So we need to show that is an isomorphism, right? And notice we are sending M by N matrices to itself, right? And the other thing to notice, and this is important, is that if you're going from something to itself, do you remember, do you have to prove, so to prove isomorphisms in general, you have to prove one-to-one and you have to prove onto. But what makes it a little bit easier for this example? Do you remember?
Isn't there a TFAE for this?
Yeah, and
Like
how'd that
ice-
TFE go?
One of them is A is invertible and A is an isomorphism.
We don't have invertible yet. That's not the TFE that we got. There's a different TFE.
Oh, okay. I'm thinking about the original TFA. Sorry.
There was a TFE for linear transformations on Rn, but this isn't an Rn. That's the one you're thinking of, right? That was from a way back. But this doesn't work for that one hasn't been proven yet for general transformations. But it was, I think, the last thing I did on Wednesday. That's a hint, if I remember right. It was the last theorem we had, and it did have TFE. The following or equivalent, I actually wrote it out. And remember it? Okay, so if you don't remember, I'll tell you. And first thing is by the, I'm going to write LT TFE. So the TFE about linear transformations. What we do know is that it is enough to just show that T is one-to-one. Okay, and by the way, it's enough to just show T is onto. So there was a TFE that said that if the dimensions of the spaces, the domain and the range space are the same, and if you want to show that you have an isomorphism, then you don't have to show both one-to-one and onto. You only have to show one of those. And you remember? Do you remember that? Do you remember it happened?
Yeah.
Yeah, I promise you it did. So that saves us 50% of the work. Okay, to write that one sentence. So it was totally worth it. All right. I think I'm gonna go. I think I'll do one-to-one because that's easier. So let's go for one-to-one. Now there was another theorem that said that we can prove that T is 1 to 1 by showing what? Do you remember?
As t of 0 equals 0.
Yeah, we have to show that, well, not T of 0 equals 0, because that's always true for any linear transformation, whether they're 1 to 1 or not. But that if T of V is 0, so let me write down this goal. T of V equals 0 implies that V equals 0. That might be what you were thinking. Do you remember that theorem that we had that too? So I'm using theorems is what I'm doing.
Yeah.
Okay, so that's our goal. So now let's just do it. So suppose that T of, in this case, V is a matrix. So I'm going to use M equals AM equals 0. Any questions so far? Okay, so that's what we've got. All right, what haven't I used yet that was given in the question?
A is invertible.
Yeah, so if A is invertible, so let's write this down. If A is invertible, then AM is equal to 0. What can we do?
Left multiply by A inverse.
Yeah, so we can left multiply by A inverse, and now I got to write it as an equation with the inverses. Just a minute. So A inverse AM equals A inverse times 0. Okay, but what is A inverse times A?
I.
Right,
Yeah,
so that
then-
means that IM is equal to, what's A inverse times 0?
0 matrix.
That's the 0 matrix. All right, and what's IM?
It's just M.
Yep, so M equals 0. Any questions on that argument right there? Okay, now that we know M equals 0, again, that was our goal. It's always good to look at our goal. M is V in this case. So therefore, T is invertible. Sorry, T is, yeah, invertible. An isomorphism, sorry. Any questions on that? Okay, I also need to go the other way. Okay, and that is that I need to show that if T is an isomorphism, then A must be invertible. Any questions on that? Because again, it if and only if means you have to show it both ways. So if and only if means I have to go forwards and backwards. So now we're going to say let T be an isomorphism. So I want to show T is invertible, right? I mean, A is invertible. Any ideas?
Show that if T is an isomorphism, then that means that it's 1 to 1.
Okay, and how do we do that? I mean, so we know that T is 1 to 1. So let's write there. Not show, we can conclude that because that's a theorem. I mean, that's part, really is part of the definition. Therefore, T is 1 to 1. But again, my goal is that A is invertible, right? Right, I need to show that A is invertible. So any thoughts? Okay, so if you don't know, I think the easiest way of doing this one is by contradiction. If A is not invertible, then by the true TFAE, that means that the kernel of A is non-trivial. Any questions on that? Okay, well, if the kernel of A is non-trivial, then let's let M be the matrix of columns that are all in the kernel, and actually write non-zero. That are all in the kernel of T. Oh, sorry, of A. Then what is AM? If A is just a matrix whose columns are all in the kernel of A, and you take A times that matrix, what do you get? What happens if you take
zero?
A times the kernel? You get zero. You get a zero matrix because A times every column is just zero. That's what kernel means. And if all the columns are in the kernel, that means AM is zero. This is a contradiction. Since T is 1-to-1. Right, a 1-to-1. So M is non-zero matrix. So that means that T of M cannot be zero. So therefore, when you have a contradiction, that means what you assumed is wrong. And what we assumed is that A was not invertible. So A is invertible. Any questions on that? Did I lose you? It's really hard for me to know whether you're all following when all I see is your name. Any questions at all? Okay, this isn't the only way of proving this, but this is one way. Okay, are there other questions about anything else?
Do you mind going over part D on problem 1 for 9.6?
Okay, like I said, the good news is I already have it, so I don't have to go and copy and paste. When I wrote it, then I've got it. So part D on number 1.
Yes.
So let V be the vector space of M by N matrices, and W the space of N by M matrices, and let T of M equal M transpose. And let's see what the question was. Determine which are linear transformations from V to W. So is taking the transpose a linear transformation? Is a big question, right? Does that make sense?
Yeah.
Okay. So to show something's a linear transformation, the first thing we can do is note that dimension of V is equal to what? We talked about this last time, a couple days ago. V is a vector space of M by N matrices. What's the dimension of V?
It's n, right?
N?
N.
No, more
M.
complicated.
M times N.
Yeah, it's Mn. M times N. Do you remember we had that last time?
Yes, I remember.
Okay. What is the dimension of W?
NM.
Yeah. So that one is, and actually maybe I'll write it. So the other one was Mn, now it's Nm, but these are numbers. If you take M and multiply by N, how is that different than taking N and multiplying by M?
It's not.
Right. So therefore, the dimensions are the same and we can use the TFAE theorem. So we only need to look at 1-to-1 or on to you choose. Any questions on that? So that's good news. It saves us half the work. And I'm always into saving half the work if I can. So whenever if you want to see if something's an isomorphism, take a look to see if the dimensions are the same first, because that's usually easy, not always. Oh, I'm sorry. This one's linear transformation, not isomorphism. Sorry about that. So for linear transformation, still good to know whether it's an isomorphism. Okay, which it turns out it is, and we'll see that in a minute. So is it a linear transformation? So let's look at it. What's T of, how about AB? Oh, sorry, A plus B. By definition, what is T of A plus B?
T of A plus T of B.
Well, that's what we're hoping for. But by definition, what's T of A plus B?
That's T of A plus B transpose.
Everything's good except there's no more T.
A plus B transpose.
It's A plus B all transposed. Got to put the equal sign. Okay, but what can we do with A plus B transpose?
A transpose plus B transpose.
Yeah, we have that theorem. It's not a very hard to prove theorem. So that's A transpose plus B transpose. Okay, but A transpose is T of A by definition. And B transpose is T of B. Halfway there. I'm going to erase this note because I was thinking about isomorphism because I was on the next section. Okay, so that was number one. Maybe I'll write 1. And now I got to go to number 2. Do you remember what number 2 is to show something linear transformation?
The multiple of a constant.
Yep, T of Ka. Okay, so now let's do that. So T of Ka by definition is equal to Ka transpose. Is that clear?
Yes.
Okay. Now, do you remember theorem about when you have a constant times A transpose?
You can pull out the constant.
Yeah. And A transpose is T of A. So that's equal to K times T of A. So therefore, T is a linear transformation. Transformation. Did I lose you anywhere?
No, that makes sense.
Yeah. So if you want to show the linear transformation, you show 1 and 2. And we've had a different one. We've had a lot of 1 and 2 in our class. Have you noticed? They're all kind of similar. To show it's a vector space, there's a 1 and 2. To show it's a linear transformation, there's 1 and 2. So, and they're both almost the same 1 and 2s. Okay. Any questions on part D? Okay, let me get to new material then. And the new material is only kind of new because you really had all this, and I think hopefully you'll agree. Otherwise, you just forgot everything because it's all the old stuff that we've done, but now we're doing it for general. Okay, so here's the definition. Let T be a linear transformation from V to W. Then the kernel of T, which is often written as KERT, is a set of all elements V in V such that T of V equals 0. Does it feel like we've done this already?
Yes.
Yeah. I mean, it's exactly the same definition. We're just now thinking of it as a general linear transformation instead of a special, linear transformation that was on Rn, but it's no different. And then, just for fun, the image of T, Im of T, is a set of all W and W, such that there is a V in V, such that T of V equals W. Any questions on that? Any questions? Is that clear? So given a linear transformation, you can talk about the kernel and the image. So maybe I'll do one just for fun. So let's let T go from P sub 2, right? Polynomials of degree 2 or less to M 2 by 2. Be such that T of ax squared plus bx plus c is equal to, we need a 2 by 2 matrix because that's where it goes. A, B plus C. Come on. C, B. Okay, is that a linear transformation? What do you think? So is that a linear transformation? Any thoughts?
I'm thinking yes.
Yeah, there's definitely linear transformation. There's no like constants, we're not adding 7 or something. That messes everything up because then notice 0 goes to 0. There's no problem with that. And if you have, A1 plus A2, that'll split it up with matrices, and same thing with a constant multiple. So everything works. But so that's one thing, just a refresher that is linear transformation. But what do you think my question is? The real question.
Find the kernel and image.
Yeah, find kernel of T and the image of T. Okay. Okay. One thing that helps, by the way, is to recognize what creatures these things are. If something's in the kernel of T, what is it? Is it a number?
No, it's a vector.
What kind of vector?
It's a vector in B. So it's a P2 or yeah, ax squared plus bx plus c.
Yeah, it's a polynomial. So it's if you so my recommendation is the first thing, just recognize what you're looking at. And what we're looking at are polynomials. So the first thing, the kernel will be a polynomial, or polynomials. How about the image? What's the image going to be a set of?
Of 2 by 2 matrices.
Yeah, so the image will be matrices. So that's usually the first thing to do. Just kind of reality check, make sure that you understand it. It's not hard, but you have to just look at that so you don't make that mistake. So let's start with the kernel. So what does it mean to be the kernel?
Isn't it a linear combination of vectors that equals 0?
Yeah, in particular, it's all vectors. Not the vectors equal 0, but what about it? The vectors don't equal 0. What?
The constant.
The linear transformation of those vectors equals
Yeah, t applied to those vectors. And in particular, t applied to those polynomials, right? So that would mean that we're looking at t applied to a polynomial. Well, t applied to a polynomial by definition looks like this. A plus B, I'm sorry, A, B plus C, CB. And that must be equal to 0, 0, 0, 0. For it to be in the kernel, that's what we're talking about. Any questions on that? Okay, so that's what we've got. So now, when will that be 0, 0, 0, 0?
When A, B, C, and D all equal 0.
Yeah. So clearly A, B, C have to be 0 because the first component, A, is 0. B must be 0 because those match up. C must be 0. So that's it. So notice in this case, the kernel of t is equal to just a 0 polynomial. By the way, what do we call t when the kernel is 0?
one-to-one.
Yeah, so t is 1-to-1. Does that mean t is onto?
Not
No.
necessarily.
No, because
Okay. Even worse than not necessarily. Not possibly.
the dimensions are different.
Yeah, because if t was onto, then t is an isomorphism. But P2 has dimension 3, M2 by 2 has dimension 4. Any questions on that idea? So we know T is not onto, but we can find the image. So the image of T is not going to be all matrices. Any questions on that? So what we want to do is we want to find a basis for the image. How do we find a basis for the image? And this came from last time.
I remember there's a theorem that if it's 1-to-1, it's linear independent.
So if it's 1-to-1, there was something independent, but we don't need that one. But if it's 1-to-1, then a basis for the image will be the set of vectors that come from a basis from the domain. So I'm going to use just the polynomials, just x squared as my first vector. And that's going to give me 1, 0, 0, 0. That was if A is 1 and the other is 0, comma. And then I'm going to do, now I'm going to let A be 0, B be 1, and C be 0. So in other words, look at just X. And if that's the case, I get 0, 1, 0, 1. Then I'm going to let A and B be 0. So, and C be 1. So I get 0, 1, 1, 0. Any questions? And I guess I should put 4 letters in. Span. So it's a span of those 4 basis vectors. Any questions at all on this example? Was it hard? Okay, what do you think?
Not really.
Yeah, it's never hard to watch, is it? So my big suggestion is make sure you practice these kind of things. Make sure you practice finding the kernel and the image before 9 days from now. What's happening in 9 days?
The final.
The final. So practice these before the final. Okay,
So
any questions on this definition before we move to?
The basis of the image of T span B, right?
Oh yeah, I guess I don't need span if I have the word basis. Sorry. So the basis is these 3 vectors.
Okay, so they together as a linear combination form any B. Or
One more time.
as a linear combination, that basis we can form any vector in B.
Any
With the
vector
basis
in,
of
yeah, any vector in the image of T.
Okay.
So any vector in the image of T looks like a constant times 1, 0, 0, 0, plus a constant times 0, 1, 0, 1, plus a constant times 0, 1, 1, 0. That's what basis means, right? So usually when you're asked to find a vector space, a subspace, what you're really looking for is a basis. And that's what I found. Okay, let's go to a theorem. And that is the kernel of T is a subspace of V, and the image of T is a subspace of W. How do I show the kernel of T as a subspace of V?
We have to show it spans and it's linearly independent.
Span and linear independent, that's basis.
We need to show if it's closed under addition, if it includes the 0 vector, and if it's closed under multiplication.
That's better. Yeah. So it should include the 0 vector. It must be closed under addition and closed under scalar multiplication. Do you remember that? Okay, so first thing is 0 in the kernel of T? What is T of 0?
0.
Always. T of 0 is always 0, or it's not a linear transformation. That was part of being a linear transformation. Do you remember that? So now let's look at T of, how about U plus V? Sorry, T of, not T of U plus B. Let's look at T of U. So we want to show the kernel. So let T of U equals 0 and T of V equals 0. So suppose we have 2 vectors in the kernel of T. What do I need to find or show?
The T of U plus B equals T of U plus T of V.
That's not what I need to show. I'm going to use it, but not show it. I'm not trying to show it's a linear transformation. I'm trying to show we have a subspace.
U plus B is in B.
Yeah, so I want to show that u plus v is not in v, but in the kernel of t. Do you see? Then t of u plus v, remember, something in the kernel is if you apply t, you get 0. Well, what can I do with t of u plus v?
It's equal to u plus v.
It's not u plus v, but
T of u plus T of v.
t of u plus t of v. But what's t of u?
That's 0,
And what's t of v?
0,
And what's 0 plus 0?
0.
0. So I just showed number 1.
Yeah.
Any questions on number 1? Okay, what do I have to do for number 2? Maybe I'll even write 1. What do I have to
Show
do for number 2?
Still in the kernel of t, even multiplied by a scalar.
Yeah, so now we want to say t of ku, or how about v? And I'm hoping for 0, but what can I do? It's the linear transformation.
Q of T of v.
Yeah, that's k t of v. That's part of being a linear transformation. But that is equal to k times 0. What's k times 0?
0.
0, and I'm done. So that's the whole proof. Any questions on the proof for the kernel? Okay, how about the image?
We do the same thing.
Yeah,
Except
yeah.
now looking at the image.
Yeah, so notice that t of 0 is equal to 0. So 0 is in the image of t. And just a note, because this is kind of weird looking, this 0 here, is that equal to this 0 here? Is 0 equal 0?
No.
No.
Yeah. So again, always beware and note that this 0, this first 0 is a 0 in V. The second 0 is a 0 in W. So for example, the first 0 might be the polynomial 0, and the second 0 might be a 2 by 2 matrix of all zeros. Does that make sense? And they look nothing like each other. So beware. Okay, now we've got that. That's usually easy, by the way. The 0 is usually easy. Now we want 1 and 2. Okay, so 1 is let t of, how about u? Let's do it in, actually, let's do it this way. It's one of those I need equations. T of v1 equal w1, which means w1's in the image, and t of v2 is equal to w2. So we know w1 and w2 are in the image. What's our goal?
To show that t of v1 plus v2 is still in w.
Not quite.
Show that that v1 plus v2 is in the image of T.
w1 plus w2.
Oh yeah.
Yeah. So our goal, let's write down our goal. Is show that w1 I'll write it with a comma, and w2, sorry, not w1 and w2, w1, one more time, plus w2 is in the image of T. So that means we need to find a vector so that T of that vector is w1 plus w2. And the hint is It's an easy search. What do you think that vector might be? So we need to find a vector in V such that when we apply T to it, you get W1 plus W2. Hint is it's easy. So what is it?
T of V1.
Okay. If you take T of V1, you will not get W1 plus W2. You just get W1.
T of 0?
Okay. If you take T of 0, you get 0. That doesn't give you W1 plus W2 either. We need to take T of something and get W1 plus W2.
T of V1 plus V2.
Yeah. So let's show that V1 plus V2 gets sent to W1 plus W2. So let's write that out. T of V1 plus V2 is equal to, and what can I do? Big linear transformation.
T of V1 plus T of V2.
Yeah. And T of V1 is what's T of V1?
W1.
Yeah, W1, because it says so above it. Plus, and what's T of V2?
W2.
W2. So guess what? I just found a vector such that if I apply T to it, I get W1 plus W2. So that means that it worked. Okay. So now for number 2. So now what we want to do is we want to say, well, what about, so let's write this down. Let T of V equals W. Then we need to find a vector in V that goes to KW when applying T. What do you think that vector might be?
T of KV.
Yeah, well, the vector is KV, right? So the domain vector is KV. So notice that T of KV is equal to KT of V equals KW. And that's it. So that's the proof of the theorem. Any questions on it? Okay, so again, we have subspaces, and that helps. When you have subspaces, that means you can do anything you want to do that you're allowed to do with subspaces. So all the properties work. All right, next theorem. So if the dimension of V is n, then the dimension of the kernel of T plus the dimension of the image of T is also equal to n. Where have you seen something like this before?
Yeah.
Null space.
Yeah. Null space. When you say null space, what do you mean? I mean, that's part of it.
Wouldn't that be like bases?
Something about bases, but more something older. Do you remember? matrices. We actually had this equation already. And we had it with matrices. We had the dimension of the kernel plus the dimension of the image is equal to n, where n, if you remember, was the number of columns of the matrix. Do you remember that at one point?
Yeah, I remember a dimension of the image of T equals the rank of A.
Yeah. Yeah. So we had rank. And in fact, let's pop this in. So here's a nice definition while we're there. The dimension of the image of T is called the rank of T. And the dimension of the kernel of T is called the nullity of T. So might as well use the same words because it still works. Any questions on the theorem and on the definition? All right, I'm not going to prove the theorem right away because it turns out that with our last section that we're about to go into, the proof is immediate. And what it says, what it's going to say basically is that you can, for any linear transformation, you can look at it as a matrix. And then you just use the theorem about matrices and you're done. Does that make sense? Any questions on that? So the proof of the theorem comes from what we're about to do. So now a review. Do you remember this picture?
Yeah.
You may not like it, but that's the way I do things a little differently than the book because I think it's so much easier. So we have this picture and I literally copied and pasted it. Okay, I just grabbed my lecture notes from a month or so ago and then just copied them into this one. But it's now different. What's different?
They are vector spaces.
Yeah, these are general vector spaces instead of vector spaces in Rn. Okay. Does it really matter? And the answer is it doesn't. Does that make sense? So here's the deal. Okay, and this is very powerful. Every finite dimensional vector space of dimension n is isomorphic to Rn. Why is that true?
Because we have that theorem that said if they have the same dimension, they are isomorphic.
Exactly. And I hope you all know the dimension of Rn is n. So if you have a vector space of dimension n, then it has to be isomorphic to Rn. Is that clear? Okay, so every finite dimensional vector space of dimension n is isomorphic to Rn. So that means that if we have a linear transformation, for example, going from polynomials to matrices, like the one we just did, I'll scroll up to remind you. That was this one. Yeah, this took a polynomial to a matrix, but this is really equivalent to the following. T of the vector a comma b comma c is equal to the vector A comma B plus C comma C comma B. Any questions on how I could take this linear transformation that sent things in polynomials to matrices and then rethink it and write it as a linear transformation that sends R3 to R4? Do you agree it's the same thing? What do you think?
Yeah, it makes sense. They are equivalent.
Yeah. So they're equivalent. It's no big deal. It's easy. The only thing that you got to be careful of is reading it. Okay? Because I wrote it as ax squared plus bx plus c. That's not always how you read polynomials. Sometimes you want to read it in increasing order, right? A plus bx plus cx squared. So if you want, for example, if you're thinking power series, then you want to increase the order of x instead of decrease. And matrices. Here I read the row, first row, then the second row. How else could I read a matrix? That's normal.
Just read the second row first.
That
Second column.
wouldn't be normal at all. That'd be weird. What's another way that people sometimes read a matrix besides by rows?
By columns.
Yeah, by columns. Okay. And, it's not like one is right and the other one's wrong. It's whatever's more convenient is the one you should look at. Does that make sense? So if you read it by rows versus reading it by columns, what you're doing actually is you're changing the basis. Does that make sense? Because bases are ordered. So if you read it by rows versus columns, you've changed the order of the elements in your basis. Similarly, if you read it in decreasing order versus increasing for polynomials, you're changing the basis. Any questions on that? So what we want to do is we want to think about change of basis. Any questions so far? All right, so now that we have that, we can do the following. We can do an example. Find the change of basis matrix. That switches reading by rows to reading by columns of M2 by 2. So what we're looking at is we have two bases. So the first basis is B, and B is going to be, well, it's going to have 4 matrices because it's M2 by 2. The first one will be 1, 0, 0, 0. The second is going to be 0, 1, 0, 0. The third will be 0, 0, 1, 0. Notice I'm reading by rows. And the fourth will be 0, 0, 0, 1. Okay. Whereas we can, in fact, maybe instead of calling it B, I'll call it R for rows. And then we're going to have another basis. Which I'm going to call C for columns. And that's going to be 1, 0, 0, 0, 0, 1. Sorry, 0, 0, 1, 0, and then 0, 1, 0, 0, and then 0, 0, 0, 1. Any questions about these are two bases for 2 by 2 matrices? How do I find the change of basis matrix? So first thing, what is the dimensions of the change of basis matrix? What are the dimensions going to be?
It will be 4.
Yeah, it's going to be 4 by 4. Because if you're going from a basis of 4 elements to a basis of 4 elements, that's going to be 4 by 4. So let's make a 4 by 4. Any questions on that? Okay, now let's go through and read the columns. This is the easiest way. The way you read the columns is you say, where does the first matrix go? It goes to 1, 0, 0, 0. Whoops. The second one goes to 0, 0, 1, 0. The third one goes to 0, 1, 0, 0. And the fourth goes to 0, 0, 0, 1. And that's my change of basis matrix. Any questions on that? Does that look pretty easy? What do you think?
Yeah.
Okay, so now what I'm going to do is get a little harder one. Still pick M2 by 2 because that's easy enough. But now I'm going to, how about A and B instead of R and C? And let's suppose it was 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1. And how about this last one? 0, 0, 0, 1. And then B is, how about 1, 2? 1, 0, 0, 3, 1, 5, 0, 2, sorry, 2, 1, 1, 1, and negative 1, 6, 7, 8. This one's harder. Do you all agree? How might we do it? Any thoughts? Any ideas?
Maybe instead of start from A to B, go from B to A.
That's not much easier. That's about the same. Here's a hint. What do you see? Do you remember doing this?
Yeah.
So you
Yeah,
first,
this is the chart for change of basis.
yeah, so you first go to Rn and then go to VT. Does that make sense? So, and remember, these are functions, so you read from right to left. So first you do this A matrix, and then you do the B inverse matrix. Does that make sense? So it's actually not that hard. I'm going to copy paste this matrix just so I don't have to redo matrices. So the A matrix is 1, 1, 0, 0. I'll read rows. You could read either way, but you have to be consistent. And then 1, 0, 1, 1, 0. And then 0, 0, 1, 1. And then 0, 0, 0, 1. Then I do the B matrix, but I do the B matrix inverse. And remember, you read right to left. There we go. And the B matrix is 1, 2, 1, 0. Zero, 3, 1, 5. 2, 1, 1, 1. And negative 1. 6, 7, 8. Okay. Next Friday, do you think I'm going to ask you to do this by hand?
No.
No, I'm not that evil. Definitely not. Okay. But you should know how to do it. Does that make sense? Not by hand, but you should know how to set it up and then put it in Symbolab and, write down the answer. Any questions on that? Easy enough? Okay, let's do something interesting. Let's suppose I should say, how about let T be the, all right, linear transformation from M 2 by 2 to P2. Oops, didn't get there. That's that. T of a matrix ABCD is equal to bx squared plus a plus d x minus b plus c. Any questions on that? And let A be the basis. X minus 1. Oops. X squared plus 1. And x squared plus 3x. And B be the basis. I guess I should go the other way around. Sorry about that. Make that one be B and the other one be A. Because the first should be 2 by 2 matrices. Let's grab one of these. How about this one? We'll use that same basis. Find the matrix for the linear transformation with respect to bases A and B. Do you understand the question? Any questions on the question? All right, how might we do this? Any thoughts?
Probably go to Rn first,
Yeah, we're going to go Rn.
then B inverse.
Yeah, so what we're going to do, and the easiest way, I think, is to go back to this. So we have the strained basis. Send the strained basis to Rn. Then do the T. And then go to the new strained basis. And remember, you always read backwards. So you'll first do D inverse, then you do G, and then you do A. Any questions on that idea?
So G will be the linear transformation on A.
One more time.
So G will be the linear transformation on A when we have A in Rn.
Yeah, kind of the easy one.
Okay.
Okay, so let's do it. It's not that hard, I promise. Where am I? Here we go. So let's go to that guy. Okay, so the first thing is you're going to change the matrix basis. So we need a 4x4 base matrix. Which takes a moment. And I'm just going to read off rows. So 1, 1, 0, 0. And then 0, 1, 1, 0. And then 0, 0, 1, 1. And then 0, 0, 0, 1. Okay, then, and remember, then means to the left. Then we're going to do the T matrix. What are the dimensions of the matrix for T? They're not 3 by 3, by the way.
4 by 4.
No, they're not 4 by 4 either. Good try, though. Remember, T goes from M2 by 2 to P2.
So it could be 3 by 1 or
Not by 1. 3 by 4. Okay, and the reason is to go from M2 by 2. That means you have to have 4 columns. To end up at P2, that means you have to have 3 rows because the dimension of P2 is 3. Now I read it. And if we just say A is 1 and the rest are 0, you get 0, 1, 0. Then if B is 1 and the rest are 0, you get 1, 0, negative 1. And then if C is 1 and the rest are 0, you get 0, 0, negative 1. And then if D is 1 and the rest are 0, you get 0, 1, 0. Any questions on that? And then finally, I take the B basis inverse. And that is negative 1, 1, 0. Oh no, sorry, reading backwards. It's going to be 0, 1, negative 1. I got to remember we're reading decreasing order. So 0, 1, negative 1. And then 1, 0, 1. And then 1, 3, 0. Anyone lost? it's hard for me to know whether you're following and whether you could do it yourselves.
I'm not sure how we got one in the middle.
This middle guy?
Yeah.
Okay, so what I did is I went back to T and I said if A is 1 and the rest are all 0, then I get 0x squared plus 1x minus 0. Is that clear?
Yeah.
Now as a vector, that's 0, 1, 0. So that's 0, 1, 0. Do you see that?
Yeah.
And then that was A, now let's go to B. So if B is 1 and the rest are 0, then I get 1x squared plus 0x minus 1. So that's 1, 0, negative 1. Is that clear?
Yeah.
So I'm using the standard bases. Standard being I'm reading by rows for matrices, and I'm reading in descending order for polynomials.
Okay. Yeah, that makes sense.
And if I decide to read by columns instead, that's fine. I'll get different matrices, but the answer will be the same, it turns out. Any other questions on this? Okay, so that's how you do change of basis, and what is a basis of a linear transformation with respect to some other basis. So here's the theorem. T is an isomorphism if and only if the matrix with respect to any bases is invertible. Why is that immediately true? Any thoughts? I don't see y'all jumping in.
I'm thinking that if we change coordinates, it doesn't change the fact that it is 1 to 1 or onto.
Yeah, in particular, it doesn't change the determinant. So remember that we're looking at B inverse. Let's say AT B. Sorry, times maybe not AT. How about T sub E times A. Isn't that what we have here? If you look at what we just did, B inverse T sub E times A. Any questions on that? But we always know that the B inverse is invertible and the A is invertible. How come? Why do we know that? Why do we know B inverse and A are invertible?
Because they are the basis for the vector space. So they
Yeah.
are.
So B inverse and A are invertible. Since they are change of basis matrices. And that we've already had. We've talked about that. Whenever you have a basis, you get the change of basis matrix is always invertible. So that means it doesn't really matter what basis you have, because if B and A are invertible, then multiplying by invertible matrix doesn't change being invertible. Is that clear? So if T is an isomorphism, then TE has to be invertible. And back and forth. Any questions on that? Because the kernel is 0. If the kernel is 0, then the matrix is invertible. We had that theorem. So that's it. That's the whole proof. Okay, now I'm going to move on to what's not in the book. We have a little bit of time left. And this is so important, I just can't not show you. Other than it changes the numbers. I hate that. There we go. So here's a very important definition. And that is, let V be a vector space. Then an inner product, let me make that red, is a function. And we put little pointy brackets from V cross V to R, such that AVW equals A times VW, U plus VW equals UW plus VW, and V comma V comma W is equal to W comma V bar. Do you remember the bar? Do you remember what bar means?
Wasn't it an average?
I guess it has been average, but not in our class. In my stats class, it's average, but not in this class.
Because that they are orthogonal.
No, good try.
Conjugates.
Yeah, complex conjugates. So if you're dealing with real numbers, the bar doesn't matter. This is only for complex numbers. Is that clear? But if you're dealing with complex numbers, you take the conjugate. Remember, like 3 minus 5i conjugate is 3 plus 5i. Is that clear? Okay, and 3, let's put that on the same page, is V comma V is non-negative and is only 0 if V equals 0. Where have you seen this before? Give me an example of an inner product that you have seen before. Many times. Where you take two vectors and then you end up with a number. What was
dot
that?
product.
The dot product. Okay, and you could look at these, and do you agree, number one, for dot product works? Do you remember that? Both of these properties are true?
Yeah.
Yeah. Okay, so number one, you had that. In my class in third quarter, in Bruce's class last quarter, you had it in both classes. Number two, you didn't have because you didn't do complex numbers, so trust it. Sound good? Does number three make sense for the dot product? What's V dot V? Do you remember? Geometrically.
V squared.
When you say V squared, what does that mean? Geometrically, what is it?
It's perpendicular.
No. Perpendicular means that when you dot, you get 0, and that's not. V is definitely not perpendicular to itself. So V dot V was the magnitude squared. So you take how long the vector is and you square it, that's V dot V. Do you remember that? Okay, and certainly 0 dot V 0 is 0. Hopefully you know that. So this is really an extension of the inner product. Okay, so why do you need an extension of the inner product when you have the inner product?
So we can do more things with it.
Not necessarily more things with it. think about our class, we have a dot product, but what if you have vectors that aren't Rn? What if your vectors are functions? What is the sine of theta dotted with the cosine of theta? Does that make sense? You'd like to be able to do that. Okay, how far apart, how far away is the sine of theta from the cosine theta? You don't even know what that means, do you?
No.
Now you will. You could talk about that. You could talk about the distance between functions, just like you can talk about the distance between vectors. So here's the big example. If V is a vector space of continuous functions, then the inner product, I'm going to use, instead of V and W, I use F and G because they're functions, is the integral from A to B of f of x, g of x bar dx. And if you're dealing with real functions, don't worry about the bar. Does that look anything like the dot product?
No.
No, it doesn't at all. But it actually is the same. This is the way of thinking about a dot product of functions. Weird?
How do we determine our bounds?
That's a good question. And here's how you do it. Whatever's convenient. But A has to be lower than B. You can't let A be 5 and B be 2. Oh, my voice is going. I don't know why. Sorry about that. So you can't let it, you have to let A be less than B. So typically, typical bounds are 0 and 1. You'll see sometimes. Any guess on what another typical bound is?
0 to pi?
Yeah, 0 to pi and 0 to 2 pi and negative pi to pi. So depending on what you're doing with it, that's how you determine the bounds. Again, we only have a few minutes left of the entire class, so I can't get into all the depth of this, but this is really important. So for example, if A is 0 and B is pi, as P is 2 pi. Then what is the length of cosine of x? Maybe magnitude is a better word. Interesting little question. How do you decide?
You integrate it
Yep.
from 0 to pi,
Yep.
2 pi.
Mm-hmm. So we're going to integrate from 0 to 2 pi of cosine squared of x dx. Do you remember how to integrate that? And you could say symbol lab, but you get 1/2. Any questions on that? Okay. Here's another question. What is the angle between sine of theta and cosine theta, sine of x and cosine of x? Is that a weird sounding question?
A little bit.
Well, how do you define angles? Do you remember? In general, we know that the cosine of theta is equal to, do you remember?
The adjacent over the hypotenuse.
Okay, but these are not those kind of vectors. You got to use dot products. And remember,
X over
V dotted with W, but now we're going to use inner product, divided by the magnitude of V, or V comma V squared. Square root. Let's see if I can make a square root happen. Yep. Times WW. Magnitude W. Any questions on that? So then you go ahead and you plug in. And I don't have time to do the whole thing, but V comma W is going to be the integral from 0 to 2 pi of sine of x cosine of x dx. Right? The magnitude of the cosine is a half. Turns out the magnitude of sine is also a half. Any questions on that? Any guess on what you get?
1.
Good guess. Actually, you get 0. Sine and cosine are orthogonal to each other. And again, you could integrate and see that. But the point is that this is a big deal. So it allows you to do geometry of functions in a linear algebra way of doing it. Any questions on this idea? I will tell you, because I want to wait till the last minute to tell you, I won't test you on this. But I would feel guilty if I didn't at least show it to you, because this is kind of an important thing. But since it's not in the book, I don't feel comfortable testing you.
Do you know a good place where we could look at this stuff that's not in the book?
I would probably go to maybe Wikipedia. Just type in inner product. So I'll write that down again. So inner product, I mean, the great thing about the internet, you can find anything. If you go to Google, I think Wikipedia might be the first one you see. But you'll find others too, whatever you like. There's videos on it. But it is 2:45. So I'm going to stop the recording.